Hello everyone, welcome to the 10th interaction session of network analysis. I'm your TA Dipanita. So today we will be continuing with our previous assignment, which was on two-port network. So in last week we saw how to calculate the different parameters such as the impedance parameter or the Z parameter, the admittance parameter or the Y parameter, and hybrid parameter and transmission line parameters of a two-port network. So in this session also we will be continuing with that. Along with it, we'll be looking into along with the already known parameters, we will be looking into how to solve a two-port network using circuit analysis. So for this interaction, what we need to know, from what we have seen last week, what more we have to know is how to look into series and parallel networks or cascaded networks. In last lecture we had seen like how to derive the input and output current in terms of input and output current and voltage, how they are related in terms of ABCD parameters, like for two cascaded network. So like last week we had seen that if there are two networks which are connected like this, where this is network 1 and this is network 2. If this is the input current and this is the final output current, so let this be V2, this be V1, this is the sending end voltage and this is the receiving end voltage. And if they are represented in terms of ABCD parameters, where these are A1, B1, C1 and D1, and for the network 2 it is A2, B2, C2 and D2, then the equivalent transmission line parameters will be T1 multiplied by T2. Which means it will be A1 B1 C1 D1 multiplied by A2 B2 C2 and D2. Now apart from this cascade connection, there may be other connections, such as here it is the series connection. In case of series connection of a two-port network, how will they be connected is, if this is the input, this is network 1, this is network 2, okay, so a series network somewhat looks like this. If this is the I1 current that is flowing into the circuit, in series network the current should remain the same, right? So this I1 current is actually coming out, which is again flowing to the next circuit. Sorry, this is I1 and this is voltage 1 dash of the first network. This is voltage 1 double dash for the second network. So the net voltage is V1, where V1 equal to V1 dash plus V2 dash, V1 dash plus V1 double dash. Similarly, in series network at the output 2, where I2 current is flowing, this is the current for network 1. The same, because it is series, the same current will flow into network 2, which you can see through this circuit, and the total voltage will be V2, where for the individual circuit, let this be V2 dash and V2 double dash. So in such of a series circuit, if we represent this in terms of Z parameter, where this Z1 will, let the Z parameter of circuit 1 is Z1, Z2, Z3, Z11, Z22, sorry, 1, 2, Z21, Z22. Let for the let this be Z1 dash for the first network, and if it is double prime for the second parameter, second circuit, so Z11 double prime, Z12 double prime, Z21 double prime, and Z22 double prime. So the net equivalent Z parameter of the two series connected circuit will be Z11 prime, Z12 prime, Z21 prime plus Z22 prime plus the, for the second circuit, the Z parameter of the second circuit, and Z22 double prime. So in this case we saw that ABCD parameters for a cascaded network, it was multiplied, but in case of a series network, this is actually the summation, just matrix summation of the two circuits. Similarly, in case of parallel, we will express this in terms of admittance. In the series network, we see that the voltage gets added up, the current remains the same. So it was easier to express it in terms of Z, because we had to satisfy this relation, that is V1 equal to V1 dash plus V1 double prime. In case of parallel network, ideally what it will be like, suppose for example this is the first network. In any parallel circuit, the voltage should remain the same, right? So then the second circuit will be, let's say this is the circuit 2. So the voltage has to be same. So if this was V1, this also should have to be V1, right? So you see, this point should be connected to this point, and this point should be connected to the other point, so that the voltage remains the same. Similarly, in this case, it will be, the port 2 will be connected in this fashion, such that the net voltage that we have here is V2, and the net voltage that we have here is V1. In this case, the input current I, on the input side, the current I gets divided into both the network as I1 dash and I1 double dash. This is network 1. Similarly, the net output current I2 will be a summation of I2 dash, which is entering the first network, and I2 double dash. So basically I1 will be equal to I1 dash plus I1 double dash, and I2 will be equal to I2 dash and I2 double dash. So in this case, when we write in terms of the Y parameter, the equivalent Y parameter will be equal to the Y parameter of the first circuit and the Y parameter of the second circuit. So it will be somewhat like this: Y11, Y12, Y21, Y22, plus for the second network Y11, Y12 double prime, Y21 double prime, and Y22 double prime. So while dealing with parallel connection, remember, write the equations in Y parameter, and while dealing with series connection, it is easier to write in terms of the impedance parameter or the Z parameter, and in case of cascade connections, we write in terms of the transmission line parameters or ABCD parameters. So let us look into a few of the problems. Initially, we'll start off with basic writing the impedance matrix so that we remember what we have done last time. For example, in this case, we have to calculate the impedance matrix for the circuit that is given here. So, writing the impedance matrix means writing these equations I2, V2 will be equal to Z21 I1 and Z22 I2. So if you are to find Z11, what we have to find is V1 by I1 provided I2 equal to 0. Do you remember this? Like last time we had done it? Are you guys following?
Yes, ma'am.
Okay. So like solve with me, like for Z11, I'm reiterating this part because we will be using it to solve the equations that we will get in this particular assignment. So I'm just doing a small problem from the previous one, which we have not done earlier. So in this case, in the first condition, when I2 equal to 0, only the circuit here that will re reduce to this. So since I1 is present, so this 8 I1 voltage will be there, but I2 is equal to 0, so there is no current flowing in this branch. So whatever I1 current is flowing here will again flow in this circuit itself as I2 is 0. V2 will be the voltage across this terminal, which is actually the voltage across this 6 ohm resistance. V1 is the voltage. So this is 2 ohm. So what will be equal to V1 if we simply look into the circuit? V1 will be equal to, what will be V1 in terms of I1?
It will be 2I1 plus 6I1.
Right. So it is 2I1 plus 6I1 or 8I1. So V1 by I1 is equal to 8. Therefore Z11, when I2 is 0, this particular condition, Z11 will be equal to 8. Then we can also calculate under the same condition Z21, where V2 by I1 with I2 equal to 0. So it is this particular same circuit. Only thing is we have to calculate V2. So what is V2?
6I1.
Right. So it is 6I1 by I1, which is 6. So how will we calculate Z12? What will be the condition for Z12? You have to just use this equation, right? So
I1
Z12,
equal 0.
Z12, I1 is equal to 0.
yes, V1 by I2 with I1 equal to 0. So when I1 is equal to 0, this voltage source will be gone. So the circuit will reduce to, since there is no current, V2 will be, V1 will be whatever the voltage drop across this 6 ohm resistor. This will also not be there. This is the 9 ohm. Since I1 0, this is gone. So I2 current and this is V2. So I2 will also flow across this 6 ohm resistor. So V1 is actually 6 I1. 6 I2 by I2, which is equal to 6. Z22 will be equal to V2 by I2 with I1 equal to 0. So V2 is 6 plus 9, right? 6 plus 9 I2 by I2, which comes out to be 15. So this is how we calculated the Z matrix. Similarly, you can also calculate the Y matrix or hybrid matrix as per requirement. So this is, the matrix is 8, 6, 6 and 15. Is this circuit reciprocal?
Yes, ma'am.
Yes, because
Yes, ma'am.
Z11 and Z is equal to Z12. Now, in case of in place of this resistance, what if we put in what if the elements are inductance or capacitance? Will anything change? Will anything change?
No, ma'am.
Right. So Z itself is impedance, right? So this be I1, this be I2. Instead of putting conditions, we will directly solve the circuit because there are very few elements. So I1 plus I2 current is flowing here. So we can write V1 in terms of I1 plus I2, right? Or also we can use the like conditions with I1 equal to 0 and all. Let's do it in the same way. So Z1 is V1 by I1 with I2 equal to 0. So can you just look into the circuit and tell me what will be the value of Z11? So I2 0 means not, this part of the branches
4
nothing,
plus 6J.
4 plus 6J into I1 by I1. So it will be equal to 4 plus 6J. Similarly Z12
J6.
will be just 6J. If you if you put the next condition with this is I2 equal to 0, right? Now with sorry I1 equal to 0. Sorry, I2 equal to 0. With I1 equal to 0, you will end up with Z21, which will be equal to again 6J. Z22 will be equal to, what will be the value of Z22?
Minus 4J.
Right. So Z22 will be equal to 6J minus 10J equal to minus 4J. So this is just letting you know, irrespective of what parameter, what element is connected across here, all the conditions will remain as it is, and you can figure out what were the uh, parameters, like impedance parameters. Now, like the earlier problem was given in terms of J, right? In terms of the impedance. Here, the circuit is given in terms of the individual circuit, element values. Like this inductor is given in 8 Henry, the capacitor is given in farads, etc. So, if you were to solve this circuit, what you have to do is either write it in terms of like S domain, or because without, if you are to write the if you start writing the equations, then it will be very cumbersome, right? There will be integral and differential equation with respect to the capacitor and the inductor, right? So instead of that, to solve circuits where individual elemental value, the values are given in terms of its elements, for example inductor in Henry or capacitor in farad, you will write it in S domain. For example, in this case, this will be equal to 8S, because this is the, you remember while we were solving a normal circuit using inductor and capacitor, we had written in case of capacitor it is 1 by j omega or 1 by s into c, right? Which is here 3s. So that the capacitor we will write in terms of 3s. This is 1s, the inductor will be written as 4s and the capacitor as 1 by 5s and this one 1 by 2s. This is V1 and this is V2. Now we can solve this circuit. So I'll be solving this circuit in two ways. One, considering this as a single circuit, and I'll be solving it. The second one, what I'll do is just to show you how series connection is done. I'll divide this circuit into two parts and solve them individually and show that it is equal to what we get from solving this circuit as a whole. So let's try this one first. Let us all calculate the Z parameters. Okay. So I1 current is flowing here, I2 current is flowing here. So the net current that will be flowing in this particular branch will be I1 and I2, right? I1 plus I2. So since we are calculating the Z parameters, let us write the equation of in terms of V1 equal to I1 some multiplication of constant into I1 plus something into I2, right? So V1 will be equal to 8s I1 plus 1 by 3s plus 1 by 4s, sorry, 1 by 3s plus 4s I1 plus I2 plus 1 by 2s I1. So if we simplify this, it will be 8 plus 4 12s plus 1 by 2s plus 1 by 3s times of I1 plus 1 by 3s plus 4s times I2. Similarly, we can calculate V2, right? What will be V2?
V2 will be
Huh.
1s I2 plus 1 upon 3s plus 4s bracket I1 plus I2.
Right. Anything else? You missed this capacitor, right?
Yes, ma'am. Yes, 5. Yes, 1 upon 5s into I2.
Right. So if we just like sort the I1 and I2 together, so it will be 4 plus s, so 5s. Sorry, let's write I1 first. So I1 is equal to 4s plus 1 by 3s. I1 plus 4 plus 1 5s plus 1 by 3s plus 1 by 5s into I2. So what will be the Z parameter of the circuit? For now we are writing in terms of S domain itself. So Z11 will be equal to, can you identify Z?
Z1,
Yeah,
Z11 is 12s plus 1 upon 2s plus 1 upon 3s.
right. So Z12 is 1 upon 3s plus 4s. Z21 is again 1 upon 3s plus 4s. And Z22 is 5s plus 1 upon 3s plus 1 upon 5s. This is what we have figured out. Now we will show like how this circuit is actually can be converted from two series circuit. We will divide this circuit from the middle, okay? So the network 1 will be these two inductors and the capacitor, and the network 2 will be the inductor and the two capacitors, right? Because if we add this two, you see this is the same point itself. So this point and this point are connected in series and we end up with this circuit. Everyone agrees network 1 plus network 2, if I do, we will get back this network. Do you follow this? Does
Ma'am, please explain little bit about how this network 1 and 2 can be called in series.
okay, so let us name the points. Okay, so let this be A, this be B, this is C, this is D. So in two-port network, like just so only the input and the output port matters, because this will be taken as the inside part of the two-port network, which we will solve for different parameters. Just look at the output ports A, B, C and D. So CD, the voltage here is V2 dash, and between A and C it is V1 dash, right? Now let this be ABCD, so let this be E, F, G and H. And the two-port network is drawn like this, right? So when we connect two networks in series, so for example like this, series connection means the current has to be same in both the network 1 and network 2, right? So whatever the current is entering through network 1, let this be I1. So of course this point is A, because the input current I1 is entering through the first network, right? What now in two-port network, whatever the current that is entering in the input side is also coming out like this. So this is C. Now for series connection, this I1 current should also be the current that is flowing through network 2. This should be I1, right? And this I1 current is flowing out. In the second, in the like the output side, so output side here is B. It is written as B. So this is B and I2 current is going in, right? And I2 current is coming out. So this is the output of the first network with along B and D. Now in case of series network, current should be same. So this I2 current itself is flowing through this network too. And the I2 current is coming out. Now for the second network, you see the input terminals are between E and G and output is F and H. So of course this terminal has to be F and this terminal has to be H and this terminal has to be E and this has to be G for the second network. Now for up to now we have not really looked into what is there inside of the network. Now this network itself I am drawing with respect to what is there inside. So we have now figured out A, B, C and D, right? So I'll draw it a bit bigger. So point C and E are same because there is nothing connected. So this is the same point, right? For the second network itself. This is C, E, this is point D, this is F, this is A, this is B, and this is G, and this is H. So in two-port network, it doesn't really matter what is inside. So I am drawing back like exactly the circuit as it was, because inside usually it is treated as a black box, but we know the circuit what is there inside, right? So I'm just drawing the connections. So there is an inductor, there is a capacitor, then there is another inductor, and this is connected to C and D. Similarly in the second circuit, so E and F are actually shorted. There is a capacitor. Just look at this is the network 2. So from here I am looking and drawing. Okay. So there is this capacitor, and from point G there is another capacitor which is connected here. There is another capacitor which is connected here. Right? This is 8S. This is S. This is 1 by 3S. This is 4S. Sorry, this is an inductor. So yeah. So this is this 4S inductor, right? In the second circuit, between E and F it is shorted, and from that point 4S inductor is coming out. So this is 4S, this is 1 by 2S, this is 1 by 5S, right? Now look at this point C and E. So C and D are shorted, so basically this point are same, C and D are same, again E and F are same. If you see, this is just a short circuit like that is there. So C and D and E and F are same. Again, C and E are also the same thing because nothing is connected in between, right? So this CE, D and F are actually the same node. This is actually one huge supernode that is there. So if I redraw the circuit like without drawing the boxes, it is just like this, right? So this is A, this is B point, right? Where the 8S and S inductor are connected. Now this is 1 by 3S. Now this point which was there like this earlier, this is the point C, right? If I just replace all the C, E, D and F, this entire point I can denote by only one point C, right? Because it is the same point itself. Because there is no other elements connected in it. Then from E and F, which I am now writing it as C, I am drawing the inductor here, right? Which is 4S. Then from there are two capacitors. One is connected to the point H, which is 1 by 5S, and there is another capacitor that is connected to the point G, which is again 1 by 2S. So this is the same circuit that we have. Is it clear now?
Yes, ma'am. Yes, ma'am. Clear.
Okay. So now for these two circuits, I'll be writing down the equations, right? And see if the series like the series connection thing is still valid. So sorry. So network 1, for network 1, let us write down the equations. So it is 1 by 3S, this is S, and this is 8S. So in series connection the currents are equal, so I'll denote this by I1 and I2, and this by V1 dash and V2 dash. So if I am to write V1 dash and V2 dash, so V1 dash will be equal to, I'll simply write the equations because this is a pretty straightforward circuit. So I1 current is flowing in here, I2 current is flowing here, so the net current through the capacitor is I1 plus I2. So V1 dash will be 8S plus 1 by
8S I1 plus 1 by 3S bracket I1 plus I2.
right. So it will be 8S plus 1 by 3S I1 plus 1 by 3S I2. This is V1 dash. What will be V2 dash? So it will be like in terms of I1 and I2. So we will consider this 5 ohm and 1 by 3s. So for I2 it will be 5s, sorry, not 5s, this is just s plus 1 by 3s into I2, and for I1 it will be 1 by 3s. So for the first circuit, the Z parameters are 8s plus 1 by 3s, Z12 is 1 by 3s, Z21 is 1 by 3s, and Z22 is s plus 1 by 3s. Now we will draw the second circuit. So in second circuit, there is an inductor connected, 4s, and two capacitors connected. So let this be V1 double dash and V2 double dash. Since in series circuit the current is same, we will write it as I1 and I2 itself. This is 1 by 2s and this is 1 by 5s. So V1 double dash will be this plus this in this particular loop. So I1 and I2, so the total current flowing through this inductor is I1 plus I2. So we will have for I1 4s plus 1 by 2s into I1 plus 4s I2. Similarly for V2 double dash, we will have 4s plus 1 by 5s I1, I2, and I1 is 4s into I1. So the Z parameter here, Z1 double dash will be 4s plus 1 by 2s. This is 4s, this is 4s, and Z22 is 4s plus 1 by 5s. So since we are saying that these two networks are in series, so the net Z will be equal to Z1 dash plus Z1 double dash. We have seen it earlier. So if I add these two matrix, what will I get? 8s plus 1 by 3 by s plus 4s plus 1 by 2s, which comes out to be 8 plus 4 12s plus 1 by 3s plus 1 by 2s. Z22 is 4s plus 1 by 3s. Then again Z21 is 4s plus 1 by 3s. And finally Z22 will be equal to 4s plus 1 by 3s plus s plus 1 by 3s. Sorry, this is 5s, right? So it will be 4 plus 1, it is 5s plus 1 by 5s plus 1 by 3s. So let us look into the first Z parameter that we had got. If you match the values of this particular one, which is 12s plus 1 by 2s plus 1 by 3s, which is what we got here, right? 5s, if you compare this one, it is 5s plus 1 by 5s plus 1 by 3s, which is equal to 5s plus 1 by 3s plus 5s. So this is one of the example of a series circuit, like which one we had initially solved it as a whole circuit, and the one individually, just to show that if connected in series, the two separate network will adapt to this, and Z1, the Z parameter of the two individual smaller circuits will be equal to the series connection of the large circuit. Did you get the feel of this series network?
Yes, ma'am. Yes, ma'am.
Okay. Any questions?
No, ma'am.
Okay. Then let's move to the next problem. So in this case, you have been given a network where the two-port network whose impedance parameters are given. Now the two ports, the input ports are connected along with a resistor and a voltage source. and the output port is connected with a 20 ohm resistor. You will have to calculate I1 and I2, which is the input current and the output current. So the the two-port parameter conditions will remain as it is, right? Since in two-port network, this part of the circuit is actually belonging to the two-port network, whose Z parameters are given, and the relation between the current and voltage will remain as it is. Only thing now is a load resistance of 20 ohm has been added, and certain input voltage with a resistance has been added into the circuit. Under this condition, what will be the value of the input and the output current is what we have to find out. So let's start. Here, since the two-port conditions are valid, so V1 is actually equal to Z11 I1, which is 20 here, 20 into I1, since the Z parameters are given in the circuit. So 20 into I1 plus 35 into I2. V2 will be 35 into I1 plus 50 into I2, right? This is the two-port conditions that will always be there. Now the new conditions that have come up is the voltage across the output voltage of the two-port network is actually equal to the the voltage across this load resistance of 20 ohm that is connected, right? So whatever the output voltage V2 is here is actually also the voltage across this load resistance of 20 ohm. So since the current direction in this way, current is I2 is flowing in this direction. So what will be the value of V2 with respect to the resistance? V2 will also be minus of 20 into I2, right? Is this fine? Did you
Yes,
understand
ma'am.
this?
Yes, ma'am. Yes,
Yeah.
ma'am.
And for the input case also, if we apply KVL across the small loop, which consists of the voltage source 20 volt, the resistance 10 ohm, and this voltage of V1, which belongs to the two-port network. So whatever that may be, so we are now applying KVL across this particular loop. So if we apply KVL, it will be 20 minus 10 into, so I1 is the input current, so I1 is flowing through this 10 ohm, 10 into I1 minus V1 will be equal to 0. This will be one of the equation, right? So the value of V1 and V2 from these two equations we can substitute in this particular equation. So let's substitute V1. So it will be 20 equal to 10 I1 plus V1, and V1 from equation number 1 we have is equal to 20 I1 plus 35 I2. This is from 1. So if we simplify this, this is 30 I1 plus 35 I2 will be equal to 20. This is one of the equation. Now putting this condition of V2 in equation 2, we get minus 20 I2 will be equal to 35 I1 plus 50 I2, right? So if we simplify this now, if we take I2 on the other side, so it will become minus 70, 50 plus 20, 70 I2 will be equal to 35 I1. So I1 will be equal to minus 2 into I2. This is the third equation we have. Now if I put this condition in this particular equation, so 30 into minus 2 I2 plus 35 I2 will be equal to 20. This is from equation 3. So what do we get? 30 into 2 is minus 60 I2, minus 60 plus 35 into I2 is equal to 20. So I2 will be equal to 20 by minus 25. Right? So it is minus 4 by 5 or minus 0.8. So I2 we got as 0.8 minus 0.8 ampere. Then if we put in equation 3, I1 will be equal to minus 2 into minus 0.8, which is 1.6 ampere. So I1 is 1.6 ampere. So the direction of I1 is entering into the circuit, whereas I2 is actually the load current. So we got it as negative minus 0.8. So the actual direction is 0.8 flowing outside. That is flowing into the load, which is ideally in case of any transmission line should be the case, because the load current should be flowing towards the load, not into the circuit. So you see, whatever the direction we had assumed for two-port network, whatever the solution we will get will balance the conditions. Is this clear?
Yes, ma'am.
Okay. Then let's move to the next question.
Ma'am, what is I1, ma'am?
So I1 is 1.6 ampere, right?
Okay, okay.
We just put it in equation 3. I2 we already got. So we put in place of I2 as minus 0.8. So in this,
Yes,
from
ma'am.
this equation 3, we get I1 equal to 1.6 ampere. Okay. Anything else?
No, ma'am.
Okay. Then let's move to the next question. So in this question, there is a two-port network circuit which is inside, which is given by the Z parameters, where input voltage is denoted by V1 and output voltage is denoted by V2. I1 current is the input current and I2 current is the output current. This is the two-port network up to this much, which is known as which is called in this question as the inner two-port network. Now towards the input side, there is this 10 ohm resistance and 20 ohm resistance connected, and towards the output side there is a 40 ohm and 30 ohm resistance that are connected. In the question it is asked, like, if we consider this big box as the two-port network, because the two-port network can contain any number of combinations of resistance, capacitance or inductance inside it. So if we consider the big box that is drawn here, what will be the overall Z parameter of the outer two-port network? Outer two-port network means whatever that is there inside this big gray color box. What will be the like the impedance parameter of this network? So the current, since there is like this is kind of connected, if you just consider this 30 and 40 ohm and consider if itself is a two-port network, this is like kind of a cascaded network. But we won't go into the ABCD parameters because only the Z parameter is given and we do not know the conversion yet. So although it can be done, but let's not go into it. We will solve it simply like we do for circuit analysis, instead of actually considering this as a cascade network. So whatever the I2 current is flowing in the outer network is also flowing in the inner network. This is the same current. Only the difference will be V1 dash and V2 dash will be the voltage of the outer network. So what we have to do is write V1 dash and V2 dash in terms of I1 and I2. In order to get this Z11 outer, Z12 outer, Z21 outer and Z22 outer. So we have to figure out this equation in order to get this matrix. So like, since we have solved one problem like kind of similar to when something is connected towards the input and output, can anyone suggest how we are going to solve this? Any
We
suggestion?
can write equations for V1 and V2 in terms of Z parameters of inner
Yes,
two-port network,
yes,
and then apply KVL in input loop of the
right,
bigger box and output loop of the bigger
right,
two-port network.
right. So this is what we are going to do. So V1 can be written in terms of the input and output current as, since for the inner loop the Z parameters are given. So we will write 50 into I1 plus 80 into I2, and V2 is 60 I1 plus 70 I2. Now we apply KVL to the input side. The input side is, so there is a two-port network connect. What we only care is about this V1 dash, sorry, V1 voltage. This is the voltage, and for the outer circuit this is V1 dash. So 10 and this is 20, I1 is flowing here. So we apply KVL in this particular loop. We will get V1 dash minus 10 I1 minus V1 minus 20 will be equal to 0. So we can substitute V1 from equation 1. So V1 dash will be equal to, so whatever the input current is, I1 will also be flowing here. So it will be equal to 20 plus 10, 30 I1 plus V1. And if we substitute from equation 1, the value of V1, it is 30 I1 plus 50 I1 plus 80 I2. So it is 80 I1 plus 80 I2. This will be V1 dash. Similarly, we will apply KVL at the output of the port where this voltage is V2. We don't care what's inside it. So in this case, in the output also there is a 30 ohm resistance connected where I2 current is flowing in this direction, and there is another resistance of 40 ohm connected. I2 will flow in this way, and this is V2 dash. So V2 dash will be equal to, if we apply KVL in this particular loop, V2 dash will be equal to 30 I2 V2, let's write it in this way, KVL. So V2 dash minus 30 I2 minus V2 minus 40 I2 will be equal to 0. So V2 dash is 30 plus 40, 70 I2 plus V2, and V2 we can substitute from equation 2. So this is 70 I2 plus 60 I1 plus 70 I2. So what we get is 60 I1 plus 140 I2. So now we have the input voltage of the output network in terms of input current and output current, and the output voltage in terms of the input current and output current. So we can compare it with the Z parameter equation, and we can write the Z parameters. So Z11 is, what is Z11?
80, it is 80.
Right. Z12 is also 80. Z21 is 60 and Z22 is 140. This is the outer two-port network impedance parameters. Is this clear?
Ma'am,
Yes, ma'am.
Yes.
Ma'am, if we want the solve of this network, why series, parallel, or cascade? Ma'am, this network in
So
cascade or series?
So no, this network is actually in cascade, but we are not going to solve this in since ABCD parameters are not given, so I have not used the cascade relation. It is given in terms of Z. In series, if you see, the series network are connected in this way. Like this circuit, if you see, so I'll maybe wait, I'll redraw it. So the difference between, okay, there is an empty page here. In case of series network, if these are the two network 1 and 2, so in series connection the current should be equal, right? So whatever the current is here is also flowing in here, right?
Yes, ma'am.
So I2 current is flowing in and I2 current is flowing out. The same current is going to the second network with I2. Only the voltage will be added. So if this is V1 dash, this is V2 dash, sorry, V1 double dash. So this V1 will be summation of these two voltage. In case of cascade network, what happens is the connection of cascade is a little bit different. Don't get confused with normal resistances that we see in series. So in cascade connection, if this is network 1 and this is network 2, this is V1, let's say, and this is V2. So whatever the output voltage, this should be I'm writing it as V2 dash, okay? And this one is input voltage, so V1 dash I'm writing. So these two voltages are equal. So the voltage of the output of network 1 is equal to voltage of the input of network 2. See, this is the output voltage of network 1 and this is the input voltage of network 2, right? These two voltages are equal. Then if current I2 dash is flowing in the first circuit and I1 dash is current is flowing in the second circuit, then I2 dash is equal to I1 dash. It will be like the negative of it. So in case of ABCD parameter, that is why we take I2 dash in this direction. So I2 dash is equal to I1 dash. So what is actually happening is output current of the first network is equal to the input current of the second network. So in cascade connection, one of the voltage and one of the current are same. In case of series, if you see, it is the same I1 current that is flowing through the entire network and the same I2 current is flowing through the entire network. V1 is equal to the summation of the voltage of the two different networks. Did you get this? Like the difference between cascade and series?
Yes, ma'am.
So in this particular situation, if you see, whatever the so if we had considered suppose only this part of the circuit as a different circuit, so the input current to this particular circuit is the output current that is flowing through this smaller inner network, right? And the voltage output voltage of this smaller circuit is actually the input voltage of this particular network if we had considered it. So this is kind of a cascade connection. But for cascade connection, you need the ABCD parameters in order to straightforward calculate the like the transmission line parameters. But in this case, the Z parameters are given. There is a conversion between Z and A, like the relation is there, but since it has not been taught, I have not solved this circuit by cascade connection. Instead, I have just simply used circuit analysis to solve I1 and I2. Otherwise, for this particular case, what would have happened is, let's say let me get a different color. So in this case, I would have considered this one to be network 1, this one to be network 2, and this one to be network 3, and solve them in cascade to calculate I1 and I2 directly. To calculate the impedance or ABCD parameters directly. Is this clear?
Yes, ma'am.
Okay. Okay, then let's move to the next question. So this is for a admittance parameter. This is related to the admittance parameter. So first network 1 is given, in which it is connected, like the input and the output of the circuit is connected as shown here, where uh, first what we have to do is determine the admittance parameter of the first circuit. Now the second condition would be the first circuit itself, two of the first circuits are connected in parallel. Why in parallel? Because if you see the voltage V1, it both appears across the first network and the second network. Only the current is getting divided. Here it is I1 dash and here it is I1 double dash. So the current is getting divided, the voltage is remaining the same. This happens only when they are connected in parallel. Similarly, in the output port, if you see, I2 dash is coming in, so the two current will flow like this, I2 double dash and I2 dash. But the voltage is same, like the voltage across this point and this point. This is the same point, right? If you see, if I consider this A, this is A, this is also A. If I consider the other part, like for example V2, so this end to be B, this is the same point B, again which is connected to the same point B. So the voltage here is also AB, the voltage across this is also AB. So the voltage across the entire set of network is same, only the current is getting divided, hence it is parallel. So for this we will like initially solve by using the formula we know, like for example, the if y is the admittance parameter of the first and y2 like y double dash is the admittance parameter of the second circuit, then net equivalent y equivalent will be equal to y dash and y double dash. We have seen this for parallel network, right? In sir's lecture also, sir has taught this, how to do it. So let us initially find for network 1 what is y. So for this particular circuit, network 1, uh, so the voltage across the output port is V2. That means the voltage across this 25 ohm resistance is V2, right? Because nothing else is connected in the output network. So this particular node voltage is V2, because this output port is actually what is there in this particular node. This is the same node itself, as nothing is connected. Similarly, this node voltage is V1, because in this element nothing is connected. So this node voltage is V1 and this node voltage is V2. Let this node be 1 and this node be 2. Now, in order to solve for admittance parameter, I'll write KCL. If I apply KCL at node 1, can anyone tell me what will be the equation?
I1
I1 is equals to V1 by 0.2, V1 minus V2 by 0.5.
Right. Since we know the node voltages, so it will be 5V1 if I just simplify it, plus 2V1 minus 2V2. So I1 is equal to 7V1 minus 2V2. Simply again we apply KCL at node 2. So I2 will be equal to, what will be I2? Plus V2 minus V1 by 0.5, right? So this will be 4V2 plus 2V2 minus 2V1. So this is minus 2V1 plus 6V2. So what will be the admittance parameter of the first network?
It will be 7 minus 2 minus 2 6.
Right. Now if you are to calculate for this entire network 2, what will be the value of the admittance parameter for network 2? By using simple formula.
It will be added double.
Right. So it will simply become 14 minus 4 minus 4 and 12, right? This will be the admittance parameter of the outer network, right? Is this clear? I'll just show
Yes.
you, yeah,
Yes, ma'am, it is clear.
I'll just show you like how it will come. Just consider this network. Okay. Since this network 1 is connected twice in parallel, so for example, let this be the first network. This is suppose the first network 0.2, 0.5 and 0.25. The second network is the same network that is connected, so I'll just draw it. So in case of parallel, this point is actually connected to this point. Again, this point is connected to this point, right? And this is connected to this, and this is connected to this. And this is V2 and this is V1, right? Now, just if I put names here, like for the nodes, let this be node A. I'll use a different color, wait. So let this be node A, this is B, this is suppose C, and this is D. This node itself, since nothing is connected across here to here, so this is also node A, this is also node B. Then this C node, nothing is connected here, so this is C and this is D. And this output is connected to C and this output is connected to D. This is the input, this is A and this is B. So the net network, if I draw, this is input A, between A and C is the input, and between B and D is the output. Now between A and B, there is this resistance 0.5 ohm connected. Also between A and B, another resistance of 0.5 ohm is connected. So between A and B itself, that means it is parallelly connected to the 0.5 ohm resistance that is already there. Similarly, just check between A and C. So between A and C, this 0.2 ohm resistance is connected. Also, between A and C, this 0.2 ohm resistance is connected. That means they are connected in parallel. Then between B and D, 0.25 ohm resistance is connected. Also between B and D, for the second network, 0.25 ohm resistance is connected. C and D are short circuited in both the network. So equivalent to what we had, the two parallel network, it can be reduced to this. Now when two resistors are connected in parallel and they are same, so R equivalent will be equal to R into R by 2R, which is R by 2. So this network can be reduced to a simple network which will have 0.5 by 2, that is 0.25, then 0.2 by 2, which is 0.1, and 0.25 by 2 is 0.125. So this can be reduced to a network where this is I1, this is I2, this is V1, and this is V2. This network. Now if we simply calculate uh, the Y parameter, so in this case if you see this node voltage is V2, this node voltage is V1, so we can write the equations of I1 and I2, right? If I apply KCL at V1, I'll get I1 equal to V1 by 0.1 plus V1 minus V2 by 0.25. So this is 10 V1 plus 4 V1 minus 4 V2. So I1 comes out to be 14 V1 minus 4 V2. Similarly, applying KCL at V2, node V2, we get I2 will be equal to V2 by 0.125 plus V2 minus V1 by 0.25. So if I get rid of this fraction, it will be 8V2 plus this will be 4V2 minus 4V1. So 8 plus 4 is 12V2. So it is minus 4V1 plus 12V2. So if I write the Y matrix, it is 14 minus 4 minus 4, 12, which is exactly what we have got when we used the formula. 14 minus 4, 4, 12. Is this clear? I'm just trying to show you how, like, when we say it is connected in parallel, we get the formula, but how it actually happens. Is this clear to you all?
Yes, ma'am.
Okay. Then let's move to the next question. So for this question, a two-port network, here the two-port is this part of the network is inside the box. So it is kind of a two-port network in which uh, there is combinations of resistance and a current source inside the network. What you have to find out is the voltage gain V2 by V1 when port 2 is open circuited. So port 2 is open circuited means what?
I2 0.
Yes.
I2 0.
So this indicates that I2 equal to 0. So we have to find the conditions like voltage gain which is denoted by EV, that is V2 by V1 with the condition I2 will be equal to 0. So when I2 is equal to 0, only current that is flowing in here will be this 2I1 that is flowing. So in this case, only the 2I1 current will flow here because no other current is coming here. whatever the voltage V2 is appearing across the output terminal will actually be the voltage drop across this 10 ohm resistance, right? Because there is nothing, no other resistance or any other impedance parameter connected. So since this two I1 current source and 10 ohm are connected in parallel, this V2 will appear across this particular 10 ohm resistance. So this node voltage will be equal to V2, and V1 is the voltage drop across this 10 ohm resistance. So this node voltage is V1. Now the circuit is pretty straightforward and we can solve it, right? So we need V2 and the ratio of V2 by V1. So let us start off, like if I apply KCL at node 1, I'll get I1 equal to V1 by 10 plus V1 minus V2 by 10. So I1 will be equal to 2V1 by 10 minus V2 by 10. This will be I1. Now if I apply KCL at this particular node, so KCL at node 2, what I get is, like there will be three currents. One, this 2 I1 current that is coming in, and the two currents that will be in this branch and this branch. So I'll get as 2 I1 will be equal to V2 by 10 plus V2 minus V1 by 10. Now I already have I1 from equation 1, so I'll just plug it into this equation. So it will be 2 into 2V1 by 10 minus V2 by 10 will be equal to V2 by 10 plus, so it will be 2V2 by 10 if I simplify this side, minus V1 by 10. So since 10 is there in all the denominator, I'll get rid of it. It is 4V1 minus 2V2 will be equal to 2V2 minus V1. So if I bring all the V1 terms on this side, so it is 5V1 equal to 4V2. Now we need the ratio of V2 by V1. So V2 by V1 equal to 5 by 4. So I can get AV is equal to V2 by V1 equal to 5 by 4, which is, it comes out to be 1 point, carry over 1, so it is 2, carry over 2, so it is 5. So the value of AV is 1.25. Is this clear?
Yes, ma'am.
Okay. Now let's calculate.
Ma'am, excuse me, ma'am.
Yes.
There is one doubt in my mind.
Okay,
Uh,
wait.
uh,
I'll open the slide. Yeah, tell me.
Suppose at input port,
Hmm.
I1 is entering, and from input port it will be leaving. I1 will be leaving.
Yes.
And here, since the output port is open,
Hmm.
this I2 is 0,
Hmm.
and current source is giving 2 I1. So
Right.
2 I1 will be flowing here towards node V2.
Yes.
So these 2 I1s must circulate through this 10 ohm resistance and this current source.
Yes, like some part will come through here and some part will come through here.
So, ma'am, then there will be some current here also in 10 ohm resistance between V1 and V2.
Between, yes, there definitely will be current. This is
But
a,
how? Since I1 current entering at input port, and it must leave from the input port also. And 2 I1 this current source is giving, and if 2 I1, okay, okay, man, got the point.
so it will get balanced. It may be zero, it may not be zero.
Yes, 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 yes. Got the point, ma'am.
Yeah.
Some part of this 2I1 will flow through this 10 ohm resistance, and some
Right.
part may flow through this 10 ohm and 10 ohm
Right.
combination, and
Right.
come back here and in the source.
Yes.
So it is clear.
Yeah. Okay. So for the next, okay, this part is done. So next we have to find the short circuit current gain, which is the ratio of minus I2 by I1 when port 2 is short circuited. So now this particular circuit get reduced to, since there is short circuit across this particular node, so this voltage, this resistance will become redundant because there is a short circuit in parallel to it. So this resistance actually will not be like, there will be no current actually flowing through this resistance because it will take the easier path out. So the next circuit that the equivalent circuit that we will have now is a short circuit. So the I1 current will remain as it is. So this is the output port current. Only V2 here is 0 because it has been short circuited. V1 will remain as it is. This is the 10 ohm resistance. This is the 10 ohm resistance. This is 2 I1 current source. So what we have to calculate is the ratio between minus of I2 by I1. So here we can apply, like we can either apply KCL at the two different nodes, or we can simply solve the circuit because there are not much parameters here. So let's just use KVL in this time. Okay, so this I2 current is coming into the node, this 2 I1 current is coming, so the net current that will be flowing here is 2 I1 plus I2, right? What now we will do is, because we do not want to go through V1 and all, so we want to use KCL. We'll be using KVL in this loop. So so 2 I1 plus I2 current is flowing in. Now if I apply KCL here, it is I1 plus 2 I1 plus I2. This is the net current that will be flowing in this 10 ohm branch. Now I will apply KVL in this entire loop. So it will be minus of 10 into I1 plus 2 I1 plus I2. Then going through this 10 ohm resistance, it will be minus 10 of 2 I1 plus I2, and there is nothing else into the circuit, so this will be equal to 0. So it is minus 10 into 3 I1 plus I2. It will be equal to 10 into 2 I1 plus I2. I'm just taking this particular term on the other side. So this 10 will get cancelled. So it is minus 3 I1 minus minus I2 will be equal to 2 I1 plus I2. So let's take I1 on one side and I2 on the other side. So it will be minus 3 I1 minus 2 I1 I2 plus I2. So minus 5 I1 equal to 2 I2. Sorry. So if I take the excuse me, uh, if we take the ratio, so we need minus of I2, right? I'll take the negative sign on this side. Minus I2 by I1 is equal to 5 by 2. So AI will be equal to 2.5. Is this clear?
Yes,
Yes,
ma'am.
ma'am.
Yes.
Okay. Then we move to the next part of the question.
Ma'am, you can take a moment and rest for maybe
Yeah,
drink water.
Yes, ma'am. You can take few minutes break, ma'am.
just
Be
hold on, like
comfortable.
I'll
Okay,
come
ma'am.
back in a minute, okay?
Yes, yes.
Okay, hello. I hope you guys are here.
Yes, ma'am. Yes.
Yes, ma'am.
Yeah. So next, like there will be two conditions in which first a 20 ohm resistance is connected across the output port. So this is the first condition, like we will solve one at a time. So in the first case, what happens? A 20 ohm resistance is connected at the output port. We have to calculate the impedance as seen from port 1. Impedance as seen from port 1, what does it mean? What is the like what parameter exactly we will calculate when the condition of the circuit is 20 ohm connected across the output port?
Z11 and Z1.
So it is Z11, right? Impedance means
Yes, ma'am.
V1 by I1. So the impedance that will be seen from port 1 is V1 by I1. What Z12 is actually V2 by I1. So this is not what we want, because this is the voltage at the output and this is the current at the input. So this won't be the impedance as seen from port 1. In port 1 it will be V1 by I1. So now with this condition we solve for V1 by I1. So the extra condition that we have now, apart from what we had earlier, was on like addition of this 20 ohm resistance, V2 will be equal to minus 20 into I2, because I2 current is flowing in this direction. So this is the extra condition that we have now. Now we can like either apply KCL or KVL as per our convenience and solve the circuit. So in this case, what we will do is, whatever the this is the same node, this is a big super node. So 2I1 current is flowing here, I2 current is flowing here. So whatever the voltage V2 is across this, coming across this output terminal, is also the voltage across this 10 ohm resistance. It is similar to as it was before because all of them are connected in parallel. So this node voltage is V2 and this node voltage is again V1, and we will solve this circuit as we had done in the previous case with only just a extra condition, that is V2 is equal to minus 20 into I2. So let's do it. So let's write the equation I1. I1 will be equal to V1 by 10 plus V1 minus V2 by 10. And again, like if I apply KCL at node 2, it is I2 plus 2I2, I1 will be equal to V2 by 10 plus V2 minus V1 by 10. Is this clear? Earlier we only had 2I2, but now since the load resistance of 20 ohm is connected, this particular current will also exist. So this is just the extra condition in KCL at 2. Now we will solve for these two and calculate V1 by I1. So we have V2 in terms of I2, so we need to simplify the equations. So we don't really need either of V2 or I2 in order to calculate Z11, right? So in this particular equation, we will substitute one at a time. Let's substitute I2 first. So I2 will be equal to minus V2 by 20, right? So I'll just substitute this in this equation. So it is minus V2 by 20 plus 2I1 is equal to, so this is 2 into V2 by 10 minus V1 by 10. Now since we do not need like V2, we will take V2 on the one side and I1 and V1 on the other side. So I'll bring V1 on the left hand side. So it is V1 by 10 plus 2I1 will be equal to 2V2 by 10 plus V2 by 20, right? So if I take V2 common, 20 will be the LCM, so it will be 4 plus 1, 5 by 20. So this is 4. So if I write V2 in terms of V1 and I1, it is V2 will be equal to 4 by 10 V1 plus 8 I1. So let this be equation 2. Now in this particular equation, I'll plug in the value of V2 so that we get an expression in terms of V1 and I1. So here I1 will be equal to V1 by 10, another V1 by 10. So it is 2 V1 by 10 minus V2 by 10, right? And V2 I will substitute from equation 2. So it is 2 V1 by 10 minus of 1 by 10 into, it is 4 by 10 V1 plus 8 I1. This is from 2. So now I will bring all the I1 terms on one side. So it will be I1. If I take it to this side, it will be 8 by 10 I1. It is 2 V1 by 10 minus of, so I'll just cancel it. So 5, it is 2 by 50 V1. So it is 18 by 10 I1 and this LCM is 50. 10 minus 1 is 9. 9 by 50 V1. So what I need is the ratio between V1 by I1. So I'll just writing it here. So so 9 I can, so 0 0 will cancel, 9 2s are 18. So V1 by I1 will be equal to 2 into 5. Is this
Yes, ma'am, it is correct.
yeah. So if a 20 ohm resistance is connected across port 2, the impedance that will be seen from port 1 is given by V1 by I1, which is 2 into 5. I hope I have not made any mistake in between. 2 by 5, so 50. Do you see any, is there any,
Man,
yeah?
things are clear and concept is okay. So
Okay, so we can
calculation
move on,
mistake does
right?
not matter.
Yeah. So the next portion of the circuit is when a 20 ohm is connected across port 1. So we'll copy it to the next one. Now instead of port 2, in port 1 the 20 ohm resistance is connected and we have to calculate the impedance as seen from port 2. So the new circuit now is 20, this is 10 ohm, this is 10 and this is 10. This is the 2I1 current source. This is I2, this is V2, this is I1 and this is V1. Only now what we have is this 20 ohm connected at port 1. So we have one extra condition, that is V1 will be equal to 20 into I1. Sorry, minus of 20 into I1. Is this right? Only this extra condition we have right now. Rest of the two-port parameter is as it is. We now have to, so if we are to calculate the impedance as seen from port 2, what do we have to calculate? So just one small thing, I don't think we can denote this by Z11 because Z11 is only valid when, so Z11 is given by V1 by I1 with I2 equal to 0. But here I2 is not equal to 0, there is a current flowing across it. So we cannot actually write it as Z11. Z11 would have been only if it was restricted to the two-port network, that is up to this portion of the circuit. When we add an extra resistance, it's just the voltage by current ratio at the input. So in this case, impedance as seen from the input, that is, if we see from here, what will be the impedance of the circuit? So what will be the ratio?
That will be V2 by I2.
Right. We have to figure out V2 by I2. Now we can solve the circuit like normally as it is. So like the extra condition here is V1 equal to minus 20 into I1. So whatever the voltage here is, the node voltage here will be the same because it is in parallel. This is the node voltage V1. So we can apply KCL at 1 and 2. So let's apply KCL at node 2. So this is the same node V2. So I2 current is flowing in, 2I1 current is flowing in, and V2 by 10 current is flowing out, and V2 minus V1 by 10 is flowing out. Now we need only V2 and I2. So we have to get rid of this I1 and V1. So let us see how we can simplify. So this can be written as 2V2 by 10 minus V1 by 10. So from this condition, if I just write V1 equal to minus 20 into I1, so I'll just replace from equation 1, 2V2 by 10 minus, in place of V1 I'll write minus 20 into I1. So this is 2V2 by, so I'll just write it as 5. So V2 by 5 plus 2I1. On the right hand side it is I2 plus 2I1. So this 2I1 and 2I1 will get cancelled. So I2 will be equal to V2 by 5. We need the ratio between V2 and I2. So it will be equal to 5. So the impedance that is seen from port 2 will actually be 5 ohm. So clear on this one?
Yes, ma'am, it is clear.
Okay. So these were the previously rolled out assignments for two-port network, and you will have similar questions in this like in this assignment, the current assignment too. If you have anything to ask, you can. Otherwise, like this is pretty much what you will have to solve for two-port network.
Ma'am, can you summarize this problem, ma'am?
Okay,
Just a summary.
yeah. So initially we started out with this network with a two-port network where the open circuit voltage gain and the short circuit current gain are given. So these are the parameters of the two-port network, which has a condition like if you see this AV is actually one of the hybrid parameters. But like for this question, it is written in terms of as a voltage gain, which is AV, which is V2 by V1. So whenever we are writing anything considered to the two-port network, it will be it will a condition such as, for example, in this case this port 2 is open circuited, this condition is applied. That is when like the output circuit is open circuited, that is no current is flowing in it. So for that, when we are to calculate the ratio of V2 and V1, what can we do is write either the KVL or the KCL equation as per your convenience. In this circuit, we see like since the number of nodes are very low, that is this 10 ohm resistance is actually what the output voltage will be. That same voltage is appearing across this. So we have resolved into writing KCL, and we calculated I1 in terms of V1 and V2 and I2 in terms of V1 and V2. Now we only require V2 by V1, so we will have to somehow get rid of I1 and I1 and I2 from the equations. So from the two equations that we get, we substitute like I1 in the other equation, and we get one equation in terms of V1 and V2. And then we can easily solve it, like simplify it to find the ratio of V2 by V1, which is the current voltage gain. In the second case, you have to find the short circuit current gain when port 2 is short circuited. So basically here V2 is equal to 0. So if we solve for the two port network, since V2 is 0, we will get one equation which has V1, I1 and I2, because rest of the currents are there. For the second equation, instead, since V2 is equal to 0, so we will get another equation in terms of I1 and I2. Now we need a ratio between I1 and I2. So from one of the equations, what we will do is we will substitute V1 and we will get one single equation in terms of I1 and I2, which we have, I guess, yeah, for this case we have done. So we got one equation in terms of I1 and I2 and we found out the ratio. So in this case, instead of actually solving for V1, we see like if we simply use KCL, we'll be able to calculate the current in each of the branches, because there is no any unknown current that will be there. We will straightforward get the current in each of the branches by using simple KCL. So we apply one single KVL equation and we get a equation in terms of I1 and I2 current, which we simplify to get this short circuit current gain ratio. Now this is only related to the two port network up to now. Now when a load resistance is connected here, once in the output side and once in the input side separately, like these two are two separate problems. So in the first time when the at the output this 20 ohm resistance is connected, this two-port network is actually now connected to RL. Up to now, two-port network was just some black box which parameters we do not know, and this is the voltage across the output port, and this is the voltage across the input port. Now when this load resistance is connected, so basically we now have an additional condition of the output voltage. So in this case we get V2 equal to minus 20 into I2. Then the solution of the circuit, rest of the circuit is as it is. So if had we only retained the two-port network equations, that is V1 in terms of I1 and I2 and V2 in terms of I1 and I2, in that particular set of equations, like this, by this I mean V1 equal to Z11 I1 plus Z12 I2, like that. If we had figured out this equation from the start, we would have put this V2 in this particular equation, and we had solved for V1 by I1, since we need the impedance as seen from the port 1. So this ratio will be equal to V1 by I1. So we need to get rid of V2 and I2. So using the two KCL equation in this case, we get rid of V1 and V2 by, since we have three equations. This is the first conditional equation we have on addition of resistance, and this is the two KCL equation that we have. So what we need is a ratio between V1 and I1. The two other unknown parameters are V2 and I2, which we get rid of because there are three equations and two of the parameters we need to get rid of. So we end up with V1 and I1, and we figured out the impedance as seen from port 1. In the second case, it is exactly same, only change is at the input port this 20 ohm resistance is connected, so we get this additional condition V1 equal to minus 20 into I1. Now on application of KCL at node 2, we automatically get rid of both V1 and I1. We did not had to write the KCL at this node 1, because at node 2 itself both the I1 and V1 gets omitted, and we end up with a equation with V2 and I2, which the ratio comes out to be 5, which is what is the impedance as seen from the port 2. Please note that this is not equal to Z22, because Z22 would have been if nothing was connected across this port as of now. Then Z22 would have been V2 by I2 provided I1 equal to 0. In this case, I1 may not be 0, because I1 will most definitely may not be 0, because a 20 ohm resistance is connected and there has to be some current that is flowing. It may be under certain condition, it may be possible that I1 is 0, but as of now I1 is a non-zero quantity, and hence we cannot write this ratio to be Z22. So it will be just simple ratio of V2 by I2 under the conditions that are given. Is this fine?
Yes, ma'am.
Okay.
Yes, ma'am. Yes, ma'am.
Okay.
Ma'am, one thing more.
Yes.
Suppose in a two-port network,
Hmm.
till now we have discussed like here in this question at input port V1, I1 and resistances are in ohms.
Yeah.
And suppose this is a two-port network, V1, I1 given 10 ohm, 10 ohm and 10 ohm given, and V2, I2.
Hmm.
So, and suppose these are given in mho.
Okay.
These are given in mho.
Right, right.
So should we convert them more into ohms? Then things will become easy, because there is
So,
one question in the assignment, like question number 10.
okay. So, it is totally up to you. You can either write the Y parameters of the circuit. Since it is given in ohm, I have only written in terms of Z parameters. If it is given in mho, you can figure out the Y parameters of the circuit, right?
So we have to write equation of I1 and I2, no, madam. Then we will get I1 and I2 in terms of V1, V2.
So, if suppose this can also be written as 0.1 mho, right?
Yes.
So basically it is like up to you. You convert it into ohm and then write this, solve the circuit as we have done right now, or you have an option like for
Madam,
example.
can you take this example only and convert this 10 ohm into mho, V1 V2 V1 I1 at input port, V2 I2 at output port.
See, then the current will also like be different here. Like
This
if
delete this 2 I1, man. Independent dependent current source we can delete. So
so,
how to write equation for I1 and I2?
so this will be 0.1 mho,
Okay, ma'am.
0.1 mho, and this is 0.1 mho.
Okay, ma'am. This is V2 and
So in this case, suppose let's say this is V1. So
yes, ma'am. Yes.
earlier what I did, whatever the current was, let's say I dash in this branch, I dash whatever the current was, what I did was, so this was V2, let's say V2. So initially I1 I had written as V1 by 10 plus V1 minus V2 by 10, right? Right now
Yes.
what I'll do is I1 is equal to, so V equal to IR relation, IZ, V equal to IZ, you know that, or it
Yes,
is
ma'am.
I by admittance. So it is admittance into V is equal to current. This is the relation, right? So what
Yes.
will I do is, here Y is 0.1, this is Y, into V1 plus, here the voltage is V1 minus V2, and the net branch impedance, admittance is also 0.1. We'll write it like this, right? Y
Yes,
into
ma'am.
V. This is again Y into V. So the relation V equal to IZ has to be valid. Then you will
Yes.
write equation like this. Similarly, I2 will be equal to V2 into zero point 0.1 plus V2 minus V1 into again 0.1. Is this making sense?
Yes, ma'am. Yes. Clear.
Yeah.
Clear.
So if you see, you will end up with exactly what we have written earlier, which is
Okay. Okay.
here. If you see, like, where is it? Yeah, I1 equal to 2V1 by 10, V2 by 10. If
Yes.
I
Yes.
if I simplify this, it will be the same thing.
Okay, ma'am. Okay.
So you have two options, like depending on how you want to solve it. This circuit can also be solved by considering this entire part to be the two-port network and writing equations like this: V1 sum Z11 I1 plus Z12 I2, and V2 as Z21 I1 plus Z22 I2. For any network, we can write the two-port network equations, right? Considering all this resistance and this current source inside to be inside the two-port network. And then on top of it, we have to put, when we add a 20 ohm resistance on the output side, we will have the condition V2 equal to minus 2 into I2. So in these two equations, we can also input this equation and calculate V1 by I1. I have solved it plain the way you solve a network analysis. You can write separate equations for two port and then solve the circuit. It is totally up to you. So the reason why I am telling you this, if it is given in mho, you have two options: either convert it to ohm, solve the network that we have solved now right now, or you can write the two port admittance network, that is I1 equal to Y1 into V1 plus Y12 into V2, and I2 will be equal to Y21 into V1 plus Y22 into V2, and then whatever the excess condition will be, if it is a resistance or any admittance connected across it, might be like anything, then you add that necessary condition and solve the circuit. I hope like it's making sense.
Yes, ma'am, it is clear.
Okay. So anything else? So you followed what is gyrator and all those, right? Because that will be required for, I think, the next topic will be using operational amplifiers. So we'll be solving that.
We have seen the lecture, it is clear, ma'am.
Okay. Okay, then if there is anything else to ask, you can. Otherwise, we can wrap it up for today.
Okay, thank you, madam.
Okay. Thank you. Good night, everyone.